movie day tomorrow?
Today we're talking about substitution.
Yeah.
Okay? Yeah, to answer your question, we will do something fun tomorrow. Okay?
Popcorn?
Learn how to foil.
Substitution. Okay? Now, basically substitution is a method we can use to solve integrals that we normally can't solve. Okay? We sort of saw this before with the fundamental theorem questions. If you remember, for example, when I had, we solved a fundamental theorem question that looks sort of like this. We did the derivative of like 1 to like x squared of t cubed minus 4 dt. Now, if you remember, this one we had to do things differently because we're not going from 1 to x, we're going from 1 to x squared. And so we had to somehow account for the fact that it was x squared. Okay? The way we could do that is we could come through and we could say, all right, change it, don't make it x squared, make it something other, like u. Okay? But set that equal to x squared. And then we'd say that the derivative of u would be 2x dx. And so now we can redo the whole problem, okay, in terms of u.
Wait, how do you know du is tx or 2x?
This is the derivative of x squared. What's this derivative?
Oh, 2x.
2x. So basically we're just saying, what we did here was say u is x squared, but to account for the fact that we're now changing things, we have to say what the derivative of u is, which is 2x dx. Okay? And so we would end up with this now with the u in place. Use the theorem to come out correctly. We get u cubed minus 4 du, which when we stick our x's in, okay, which when we stick our x's in, gives us x squared cubed minus 4 times 2x, okay, leaving us with our answer that way, okay. Basically, what we're doing here is, and we could shortcut it, we don't need to do this for this fundamental theorem question, okay, but whenever we've been doing the fundamental theorem when it's just been x, there's been a dx tagged onto the answers that we don't do anything with because the derivative of x has always been 1, okay? And so we just kind of sweep it under the rug. But because we're no longer dealing with, things that are simply x, we're dealing with x squared here. To account for it, we have to tag on the derivative of x squared onto the end of our problem, okay? And this is how it works. And if you don't, remember too, if you have trouble seeing that this is the case, go ahead and take the regular antiderivative of this with respect to t, put in what you got, evaluate it normally, and then do the derivative of that. I guarantee you're going to get this as your answer. Okay, that's a way you can always check these things out. Okay, is to do it that way. Okay. Well, it turns out this method of replacing the offending thing x squared with a u, this is a common occurrence, and we call it substitution. Okay, because what we're doing is we're substituting u in for our equation. Okay, and it turns out I can actually do this with any sort of function. Okay, not just these involving the fundamental theorem. So we're going to look at a normal integral. Okay, in which we're going to do substitution to in a second after we go over the theorem of substitution, what it means. Yes.
Oh, never mind.
Okay. So I'm going to write out kind of the case in which you would use substitution. Okay. Let people copy. Okay. So, the theory behind this is that if I have my function, basically, kind of substitution. Let's not use this color. Let's use that one. Okay. Okay. So basically, if I have the integral of f of g of x times g prime of x dx, I could let g of x be equal to u, and g prime of x dx be equal to du, I could then rewrite this thing as the integral of little f of u du, which then gives me the antiderivative like that right there. And yes, I'm fully aware of the double entendre that's now up on the board. The book actually is the one who's responsible for this, not me. Yes. Okay.
Oh, Mr. Dowell.
But notice here, we're changing our variables to come up with our answer. So another way I can think of this then is that our answer for this thing right here, okay, would be big f of g of x plus c. Okay, and so the reason for that comes from this substitution down here. Okay, such a thing, by the way, is generally referred to as a u substitution. Okay.
So it's standard that they're using U and not.
Yeah. Again, so the standard is a u. If you use some other variable, it's fine by me. Just realize what you're doing. Okay. But the standard is u. Okay. Now, one thing I want to point out here. This right here. Okay. What have we seen before that looks suspiciously like that? As far as think derivative rules. Chain rule. Okay, the chain rule gives us that, right? Basically this is a chain rule, and you'll see some versions of this written. Instead of doing little f of g of x, g prime of x like so, they'll make this big f prime of g of x. Because remember, little f is the derivative of big F. Okay, but this is a chain rule. So what we're actually doing with substitution is we're doing the chain rule in reverse. We're turning the chain rule process around, okay, in order to calculate out derivatives and things, or intervals, okay? So this is that relationship there, okay? So basically this is the kind of the chain rule version version of the chain rule for intervals, okay? Everyone understand that? Got that down? All right, let's take a look at an example of how this works, okay? Example problem. Let's do the integral of 2x times x squared minus 4 to the 1/2 dx. As this thing is currently written, can I do this integral? No. Okay. I can't multiply the 2x through because of the 1/2 exponent. I can't factor or expand x squared minus 4 because, again, of the 1/2 exponent. Okay. So as it's currently written, there would be no way for me to handle this. Okay. But now with the substitution method, I can go through and make changes. Okay. And then make this into something I can handle. What I need to do first is figure out what I want to make u. Okay.
X squared?
It's x squared minus 4 is what u should be. But a quick way to always identify that that's going to be what you're going to pick as to be u is generally the thing with the highest exponent and or the thing that's inside parentheses, okay, should be the thing you make u. Okay? Now, this isn't always the case. There are some exceptions. We won't see many of them, and when we do see one, we'll go over it in depth, why it worked out the way it was. But for the vast, vast, vast majority of these things, you're just looking, okay, what has the highest exponent? Or you're thinking, okay, what is bound up inside parentheses? Okay? In this case, x squared minus 4 to the 1/2, that is both x squared is the highest exponent of the x's, and it's inside these parentheses. So I'm going to make that be u. Okay? So I come through here and say u is equal to x squared minus 4. Okay? Du then, whenever I declare what u is, I independently say, okay, what's the derivative of u then? So it should be 2x dx. Okay? Now I come back through and say, okay, do I have 2x dx? Yeah, there's my 2x, there's my dx. So I can do a u substitution. So I can come through here and rewrite this thing as the integral of u to the 1/2 du. Okay? U to the 1/2 du. Well, that's an easy antiderivative to take, right? What do I do to u to the 1/2? Add 1, divide by the new thing, right? Which makes it what? U to the
3 halves.
3 halves over 3/2 or 1.5. I don't really care how you do it. And then plus c.
Use the 2x in front of the x squared minus 4 and turn it into du.
That's what du becomes. In fact, if I go ahead and highlight all this, 2x dx became my du, and this became my u. Okay? Just like so. Okay? By the way, you can leave your answer in terms of u. Okay? You could go ahead and put x squared minus 4 back in for u. You can do it that way as well. There's benefits of doing it either way. It all depends on what you're doing. It depends on like what you're after, as far as the problem is concerned. Okay. Sometimes leaving it in terms of u makes sense. Sometimes putting x squared minus 4 back in makes sense. Doesn't really, when we do definite integrals, they work a little differently with u substitution. And so we'll take a look at that here in a second. But for the most part, we're done at that point. Okay, we don't have to go any further. Any questions on how that worked? Okay? Yeah?
Well, there's d there, but what happened to like 2x dx? They just...
It became part of the du. Okay? It became part of the du. When it becomes part of the du and you do the antiderivative, it just goes away. Also, too, actually this will be a good exercise to do. Let's go ahead, okay, and fully replace this, because one way you can always check your answer.
Do we not have to replace the...
Not always. Sometimes there'll be times where it'll make sense to replace it, and there'll be times where it's like we don't need to replace it. Okay, it all depends on the problem. Okay. Remember, one way I can check to see if I've done things correctly is take the derivative of my answer. I should get the integrand back. Okay? So, the derivative of x squared minus 4, okay? So this is only me just checking my answer, okay? This is a check. Okay? I'm going to do the derivative of x squared minus 4 to the 3/2 over 3/2 plus c. What rule do I have to use to handle that?
Quotient.
Not quotient rule, it's 3/2 is a constant, we don't care. Chain rule, right? Chain rule says treat the outside as if it's its own derivative, keeping the inside the same. Multiply it then by the derivative of the inside. Okay, what happens to c, by the way? It goes to 0. Okay. All right, what's going to happen to those 3/2? They cancel. Okay, and that left me with x squared minus 4 to the 1/2 times 2x. Wasn't that the integrand I started with?
Yep.
Booyah.
Yep.
Okay. So the idea here is what we're doing here is we're reversing a chain rule. Okay. The thing with the integrand we start off with is a chain rule basically. It's the result of a derivative done by the chain rule, and we're putting it back together again to what it originally was. Okay. So and that's why the 2x dx when it became the du, we don't have to account for it anymore. It just gets kind of swept back into it because that was part of the chain. Okay. We're breaking the chains. Okay. I don't know. Seems silly enough to say. All right. Any questions now? Makes more sense? Okay. There are some times where you can run into issues. Let's look at an example where you have a little bit of a problem. Okay. And we're going to keep it with, again, we're just going to do simple examples. I mean, these things can obviously get more complex, but we'll keep it simple. Let's look at this one. The integral of x plus 4 times x squared plus 8x minus 5 to the 6th power dx. Okay? All right. Right off the bat, what do you think u should be?
X
X squared plus 8x minus 5. That's the most complex thing up here. It's also the thing that's in big parentheses. I mean, yes, x plus 4 is also in parentheses, but it's not as complex. So we'll make u equal to x squared plus 8x minus 5. What's du then going to be?
2x.
2x plus 8 dx. Uh-oh, spaghetti-o. Got my dx. I don't have 2x plus 8, I have x plus
Factor
4.
out of 2.
Okay. Not factor out of 2, but you're on the right track. This is half of what I need it to be. I need to throw a 2 up in there, right, to make this thing work. Okay? I could say that my du down here is 2 times x plus 4 dx. So I'm missing a 2. And you're,
du over 2.
okay? I could put du over 2, or a better thing is, can't I just stick a 2 in?
Yo.
I can, as long as I put a 1/2 on the outside. Why would I do that?
Because
I'm just multiplying by 1. I don't change the value of anything. Okay? I can come through here and say, okay, I need a 2, let's put a 2 in there. But if I did that, I gotta account for the fact that I changed the value by putting its reciprocal on the outside.
Oh, that's where you put the constant.
Yes. And this goes back to, if you remember, we were looking at integral properties. Okay? I wrote one of them was the integral of a constant, f of x dx is equal to the constant times the integral of f of x dx. And I said that's probably one of the more important properties. It seems really easy, but it ends up being super powerful and kind of probably the one you're going to use the most. This is why, okay? All I did here was stick, basically, I didn't change the value of anything, okay? I can put the 1/2 and the 2 inside and outside the integral all day long, okay? But I'm doing it in such a way in which I can now do my u substitution, okay? Because 1/2 times 2 is 1, doesn't change the value, but because of this property right here, I can have the 1/2 be on the outside and the 2 on the inside, letting me get away with what I want to get away with.
So it doesn't affect the second parentheses?
It will not affect anything at all, okay? Because that's 2 times a bunch of stuff. Remember, when you multiply by 2.
In front of everything.
Yeah. Okay? And the 1/2's outside to cancel out the 2. Okay? So now I can do my u substitution. Okay? The 1/2 is still going to stay on the outside because it's outside the integral, so it doesn't get substituted for. But the 2x plus 4 dx, that becomes du. And the x squared plus 8x minus 5 to the 6th, but that becomes u to the 6th. Okay? And so we started with something we couldn't do, made a change to it using a property that we know, and now got into something that's really easy to do. What's this thing's antiderivative going to be?
U to the 7 over...
U to the 7
over 7.
over 7 plus c. The only thing we need to add on this
What times 1/2?
is put the 1/2 out in front.
Freaking...
And the 1/2 really, I mean, you can put the c on the inside, the outside, it doesn't really matter because it's still c in the end. Okay? 1/2 c is still c. Okay? As far as integration is concerned. Alright? And so now we've got the antiderivative. And I can leave my answer like that. I can put in the, what originally it was, I can put that in there. There's lots of different things.
You don't even need to plug it back.
Wait, you don't have to multiply 1/2 by 2?
No, well, I mean, you can, it just doesn't make a difference. 1/2 c is still c. Okay? It's an unmentioned constant. If I was actually figuring out what c was, then yeah, I'd have to do that, but... Well, even then, actually, I wouldn't still have to do it, because if I was figuring out what c was, I'd be given a point, and I'd just have 1/2 bunch of stuff plus c still, and just, you know, figure out c independently. Yeah, the whole c on the end is more of just, it's an accounting trick. It's just we know there has to be some constant on the end, and we don't know what it is. So it doesn't matter, I could do anything I want to c, I'm still going to just be a constant, so it's still just c. So that's why I've written it the way it was. Okay? But that's how we can handle something we normally couldn't deal with. Okay? We had something that was impossible to do, made a change to it, made it possible, made it work. Okay? Again, all from that one property. So keep that in mind. And if I want to leave that as u, I can leave that as u. If I want to make it x squared plus 8x minus 5, I can do that as well. Okay? All right? Any questions on how that works? Okay. We've got 5 minutes left, so let's go over the final thing that has to do with substitution. Okay? And this is what happens with definite integrals. Okay? Substitution with definite integrals. Okay? Basically, if I have a substitution problem with definite integrals, I have to change the numbers when I do a U substitution. So if I had the integral from a to b of the whole f of g of x, g prime of x, dx, I think that would be nicer, okay? Basically, if I had the thing, okay, when I do the u substitution, by saying u is g of x and du is g prime of x dx, the numbers a and b can't stay as a and b, okay? They have to be changed because I've changed the function, okay? If I kept them as a and b and then evaluated it in terms of u, I would get an answer that I would not be getting the correct answer. Instead, what I do is I basically figure out what their u counterparts are. I basically put them into the whole u part to figure out what they are. I basically say what's u is equal to g of x, so what's g of b and what's g of a, and that would change it to u. Okay, so this down here would become g of a. Up here would become g of b, as I did my u substitution. Okay. All right. Working them out. Yeah. So what you do is you basically change the numbers accordingly. Let's look at an actual example of this working, so you get the idea. Okay. We'll keep this one simple. We'll go from like 1 to 5 of 2x times x squared to the third dx. Yes, I know that's an easy function. You don't actually have to do a u substitution. You could do that one easily by just cleaning it up. But for the sake of example, we're going to do it this way, okay? I'm going to say u then is x squared. Du would be 2x dx, okay? That would make this then u cubed du. These numbers there, though, can't stay as 5 and 1, okay? So what I do is I figure out what they are in terms of u. I would say u of 5 is equal to 5 squared, which is 25, and u of 1 is equal to 1 squared, which is still equal to 1. So this becomes 1 to 25 now, okay, when I change things, okay? Now when I do my antiderivative, everything works out nicely. Okay? And I can evaluate it directly. Okay? By the way, if I didn't make the change and instead opted to substitute back in x at the end, okay, I would go back to my original numbers 1 and 5 and note what's going to happen now. So if I did it that way, okay, kind of this other way, okay, right here I would say u to the 4th over 4 from 1 to 25 will be equal to x squared to the 4th over 4 from 1 to 5, okay? But when I evaluate that, I'm going to have 5 squared to the 4th over 4 minus 1 squared to the 4th over 4. And what's 5 squared?
25.
25. So note what happened. Did anything actually change? No, I still ended up with the same thing. Okay? So it doesn't matter whether I do this or not. I'll get the same answer in the end. But note, if I wanted to keep things in terms of u, I have to make this change. Okay? Yes, Lou?
How did you get the minus 1/4 over 4
At the end?
Yes.
It's the way definite
F
works.
of B
Remember?
minus F of A.
F of, yeah, F of
Oh.
B minus F of A. F of big B, or big F of B minus big F of A. That's how I end up with the minus. Don't forget, okay? And that's really the only difference between this and doing it normally. So you could keep the numbers the same, but realize you do have to stick x in at the end, or you could quickly change the numbers and didn't do everything in terms of u. It's up to you.
What is that?
Oh, that's a 5. Sorry.
I'll just move
The
it.
stupid,
What is the AP problem on?
the AP problem is on basically Riemann sums. Okay?
Let's do tomorrow.
Yes, do tomorrow. It's a position acceleration velocity problem. Okay? But using Riemann sums, it's actually really pretty straightforward because you just have to know what a Riemann sum is. And everyone knows Riemann sums. Okay.
Thank you.
You're welcome.
Thank you. And I had to BS that.